G'day guys. Today we're looking at earthquakes. It's going to be our first lesson, and for it we're going to be using the earthquakes PowerPoint. It's just earthquakes 2020. So let's start off by asking ourselves, I'm going to write down some questions. What are earthquakes? What are the causes? Where do they occur? All right, so what are earthquakes? Well, earthquakes are any sudden earth movement. The causes of earthquakes, well, there's a number of causes, but primarily they're caused by tectonic movement. If we think about the crust as being fairly, or the lithosphere I should say, as being fairly brittle, it is prone to, I guess, sudden movements as we've got a great deal of movement going on underneath it. Rigid and brittle will move due to the moving asthenosphere. This is the asthenosphere. Great. Where do they occur? Well, you're going to know the answer to this, but earthquakes primarily occur on plate boundaries. So let's look at our types of earthquakes. Let's look at our collision. So the earthquakes in a subduction zone are shallow to deep, as we know. In a collision boundary, they are fairly shallow. So in divergent boundaries, they're primarily shallow and they aren't very strong. In transform boundaries, they are definitely shallow. They cannot go deep, but their movement can be very strong. Collision boundaries, shallow, but not as strong. And our subduction boundaries, they can be shallow to deep and very strong. All right. So what I would expect you to know for each of these locations is a place in the world where these earthquakes could be happening. Now let's do that in red. So let's think of a location and let's go with our collision boundaries. So a location for our subduction would be Indonesia or Japan. Now, two of the world's largest earthquakes ever to occur occurred in these places, in Indonesia in 2004 and in Japan in 2010. Both events triggered a subsequent tsunami which killed many, many people. In the case of this one, we have the Boxing Day tsunami, and this one, the Fukushima. All right, transform boundary locations. Well, our best example is the San Andreas Fault. And that's in California. Divergent, well, again, we can think about Iceland. We can think about the East African Rift. And we can also think about within some oceanic regions, there would be micro earthquakes that would be occurring at depth, deep under the ocean. All right, so these are locations where earthquakes are commonly occurring. Remember, subduction and our transform are our two primary types of earthquakes that we're going to be looking at here, and our two of our most destructive. Collision, if we're thinking about a location for collision, we're looking at the Himalayas. There are earthquakes, but the primarily damage that earthquakes there causing avalanches. Right, good. So let's look now at the anatomy of an earthquake. Actually, before I talk about the anatomy of an earthquake, there is something I guess I should discuss, and that is intraplate activity. And you'll notice on the PowerPoint I've put a slide on it. And this is particularly relevant for in Australia. Because Australia So the reason I guess I would mention this is because if we think about Australia, we don't get many earthquakes at all. The reason is because obviously we sit right in the middle of the Australasian plate. Now we have had quite a few recent earthquakes. We have had, let's just talk about some of the some of the ones that you might know about or might even remember, and that is 1989 in Newcastle, in New South Wales, 2010 Kalgoorlie earthquake, and also, I guess the other one is the Meckering earthquake. And the Meckering earthquake occurred, I think it was 1968. The Meckering, of course, is in WA. If you ever get to go there, it's pretty interesting. You can see some damage and fault damage caused by the earthquake. There's a field just near the train line where if you look at the ground in one section moves down, but then if you look at it, there's actually we've actually got a small fault that you can see. It's not very big, and it's not more than a metre, but it's something good to look at, and I guess something good to know. The Meckering earthquake actually destroyed the town of Meckering, knocking down most of the shops in the area. It also knocked down some buildings here in Perth. So it's one of the largest earthquakes that we've had. So one of the reasons that we actually get these earthquakes is because of, because of the old geology of WA. So if I draw a little picture of WA, hopefully it might give you a bit of an indication. We obviously in WA, let me just say a map of Western Australia. And if I'm going to draw a really crude map of WA here, down, we sort of come down. I think I know we go out, and there's Shark Bay here. Oops, not very good, I'm afraid. Sorry. Oh, that's really bad there. All right, forgive me, please, for that terrible drawing. But one thing, I guess, here's what's interesting is right across WA, and if you think about Perth as being right down here, right through Perth, there's these lines through Western Australia, there's these lines here. And they form a really interesting thing called the Darling Fault. Now, the Darling Fault is a remnant of when we used to be joined to Africa and Madagascar. When we used to be joined to Africa and Madagascar, obviously Africa would have butted up to here, and we would have made this nice massive continent. The continent would have been Gondwana land, but then as we split apart, there was a fault line left, and I guess it was a break in the crust. And what that means is that if there's any movement of Australia or of the Australian Craton or the Great Western Craton, as we have here, GWP, Great Western Plateau, it's going to be felt along this line of weakness. It's a line of weakness. So let's get to the intraplate activity. You might remember Jürgen. This is Jürgen. Here's Lederhosen on, yes. And Jürgen likes icebergs. In fact, he goes and stands on them a lot. We know that there's a lot more under an iceberg. Well, if you take Jürgen away from the iceberg might look a bit more like this. No Jürgen. So the reason is because the Earth itself, or the lithosphere itself, will move up and down on top of the asthenosphere, and this is called isostatic movement. So it's I guess you could say, floating of lithosphere on, let's call it the mantle. Or the asthenosphere. So when there was I think if you think about Australia as being quite old, and over the time, a lot of this landform is eroding, is erosion. And what it's doing is it's removing, if we think about our iceberg, if we were to remove some of the top of this iceberg, then the iceberg would want to bob up. Just as if we remove Jurgen from the iceberg bobs up. Now this happens in nature. As sediment and dirt is eroded from the continent and material is eroded from the surface, the continent will have that isostatic balance and bob upwards. When it bobs upwards and when it moves along fault lines. Any line of weakness, there will be some sort of movement there. And here, right along the coast of the coast of WA is the Darling Fault, and it's our line of weakness. And Meckering lies right on that fault. And that's one of the reasons why this particular earthquake occurred. Kalgoorlie is a very interesting story, and the reason why some people think the earthquake happened in Kalgoorlie was because of the super pit. It's not been proven yet, but there's a bit of research on that, and I think you might want to look at that. You could also say it's an impact of the mining activity. If you're removing a large amount of dirt from one area, then essentially it could be doing a Jurgen, if you will. All right? So you can have plate activity at plate boundaries, where we've got tectonic movement, but you can also have intraplate activity caused by isostatic movement of the continent. Or let's just call it doing a Jurgen. Please don't say that in an exam, by the way. Next part is anatomy. You might be wondering, what are earthquakes made of? Well, it's not quite as simple as it's just shaking, because there's a lot more going on behind the scenes. Earthquakes come down, are really a part of a theory called elastic rebound theory. And elastic rebound theory is a theory where we have strain leading to deformation. Can I demonstrate it? Yes, let's demonstrate it with this poor volunteer pencil. If I place this volunteer pencil, if I place this pencil under strain, you can see it starting to move until there's strain, and all of a sudden, whoa, it's really going. There's deformation. Sorry, pencil. It's still good. I've got two now. So we have, within the earth, we have strain, pressure caused by the movement of two things, and then deformation where it finally faults or something breaks and we have our earth movement. So if you click on the slide, we've got elastic rebound theory. If you look at the pictures, you can look at you look at the ground, and then all of a sudden there's movement. There's the earth wants to move, and all of a sudden it does move, and there's deformation. So strain is the pressure, and deformation is the release. Different landforms and different rocks will have a different strain or different resistance to strain, and that really depends upon the geology of that area. Some areas can move around quite easily, and some materials can move around very easily, and some other materials don't. They don't have the same strength in them. All right. Let's now also look at, I guess, what happens within the area. So I'll draw a little picture here. And it's not very good. But here on the top we have a house. And there's the house there. And below the house, we've got the earth. Okay, so if we're going to have our earthquake occurring right here, this is the focus. It's the focal point of the earthquake. It is where the earthquake happens. Directly on the surface above that, we have the epicenter. We need an epicenter so that we know, I guess we've got an approximate area or gives us an indication of what's happened and where it's happened. Around the epicenter, we will have seismic waves occurring. So let's look at these seismic waves and let's look at our first wave. And our first wave is called the primary wave. Primary because it's the first. Primary waves are compressional. I want you to look up on YouTube a compressional wave or primary wave and then a secondary wave, and it will show you what it looks like. It's very hard to draw what a primary wave looks like, but if I was to try and show you with little dots, so if we got, I guess we've got some dots occurring here. Here we have some random dots, and there's some that's far apart, and then I'm going to have some that are really close together. Compression, and then we have our. So it's not a very good picture, but we've got areas of compression, all right, and areas of refractions, compressions, refractions. And this is a compressional wave. It is the fastest of all the waves, and it moves. I shouldn't use velocity, but let's just use that, at about 6 kilometers per second on the surface. It moves at about 11 kilometers per second at the core. Why? I want you to answer this for me, and you can answer this on Teams. Why is it faster at the core than at the surface? All right, that's our first wave. It's the primary wave, it's a compressional wave. Let's do our next wave, and surprise, surprise, it's called the secondary wave. Because it's second. It's I'm just going to draw a line here so I don't move over. A secondary wave is a shear wave. And then we think about shear waves, they're a nice up and down movement, side to side. That's our shear wave. They're slower. Sorry, physicists, for using velocity. They travel at about 3 to 3.5 kilometers per second. They're a lot slower on the surface. But hang on, they don't travel through the outer core. They don't travel through the outer core. Why? And I'm sure you all probably know the answer and you're thinking about the answer right now, and that's great. But I want you also to think, well, how can it measure? So how can it measure or travel through the mantle? And I guess I want you to reassure you what the mantle is actually made of. So you're all obviously going to be saying that it's not traveling through the outer core because of this reason. But what does that tell you? Tell you about the structure of the mantle. You're going to answer me that in Teams, maybe Friday. Actually, definitely Friday. Okay, so good. They're out. They're the first two parts. These different parts of the earthquake occur underground. So they're underground. UG. Done. Good. Let's look at the surface. On the surface, we have a couple of different other types of waves. So let's carry on. Let's call this what the other one was. Anatomy of an earthquake. Now, on the surface, we have two other types of waves. We have Rayleigh waves and we have love waves. Now, why were they named this way? Obviously, there was a doctor called Dr. Rayleigh who discovered Rayleigh waves. And yes, there would have been a Dr. Love who would have discovered love waves. Or maybe I'm just making that up. Maybe you need to find out. So what do they look like? Well, Rayleigh waves are really interesting because they're quite elliptical. So if we think about our up and down waves, but within these waves, we've got elliptic movement, not shear movement. So it's not, that's shear movement, but elliptic movement is, we've got sort of movement that is in an elliptical shape, all right? It is not, that looks like a person there, but it's actually, like a wave. So a Rayleigh wave is as close to a real wave as possible. Now, love waves are side-to-side movement. So if I draw a picture of a, let's see, of a house, all right. So a love wave would be that house moving side to side, like this. Okay. So our surface waves are up and down, like elliptical. Now, whenever you watch the earthquake videos, it's the shear waves, it's the love waves that you're looking at. You are seeing that side-to-side movement, and it is the most violent. Our love waves cause the most damage out of all the waves. They are what causes more deaths than anything else. It's our love waves. All right, so they are the four parts to an earthquake. When we look at an earthquake seismograph, and when you look at the next slide, I think it's slide number 15, and it talks to you about the different waves. Is it possible to see the different waves on a seismograph? Yes, it is. And if I was to draw what a seismograph would look like, it would look something like this. We would have just white noise, not much movement. Then we would have our first wave, our P wave. Now P wave, remember, it's compressional movement. It's not going to be as violent. Then we have our S wave, very closely followed by our surface waves. And the event is over. Now what's important to notice here is these times here. Here is the arrival of our P wave right here, that spot. Here's the arrival of our S wave, that spot there. And here is the arrival of our surface wave. So let's say, for an example, this is, we're in a location and it's a long way away from the earthquake. The first thing we'll feel is the P wave because it's traveling the fastest. Next is the S wave because it's going the next fastest. And finally, the slow but very violent surface waves arrive. Now, how are they measured? What do they look like? Well, they actually look like them. They're measured on an item like this. And this is a seismograph that we have at school. And when you look at it, it's a pretty simple sort of item. We've got a roll and some paper, and that moves. And then when the earth moves, we have a little mark put on the paper. Oh, and the whole thing's shaking. But this is, I guess, a very simple idea of a seismograph. You can go to the United States Seismic Survey or the Global Seismic Survey, and you can get up-to-date maps or up-to-date graphs, seismic graphs, to show you the different types of, all the immediate earthquakes that are happening at any particular time.